And can everybody see my screen or the whiteboard that I shared?
Yeah.
Okay, good. How are people doing with the log lab? Let me start there and just ask if how progress is and whether it's more difficult or it's looking okay. Anybody who want to sort of report on their experience so far? I hope lots of people have started. Maybe I'll call.
I oh,
Yeah, go ahead.
Oh, sorry, go ahead.
okay.
Oh, okay, cool.
I'll go. The lock lab. I think the first part, the KO lock
Yep.
part, was not as bad. Well, and then the second part, was a bit harder. Well, it's a lot harder in my opinion.
Yeah.
You just have to figure out a. I guess the hard part was thinking of a solution that it's like, hey, this doesn't cause deadlock, but then if you think there are cases where like deadlock could happen if you acquire a buckets lock again and all that stuff. But
Yep.
if you, yeah, you just have to think. You have to think like about extra cases and all that stuff, and after that, it shouldn't be that bad.
Okay. Anybody else who want to share their experience so far?
I wanted to ask, are we allowed to do any part of the lab like lock free? Because I know like their first part, for example, is pretty, the instructions said pretty clearly like make a parallel memory allocator, but can we do it just lock free and leave it as it is?
Yeah, you're free to do any solution that passes make grade is fine. Lock free, I would be, you could certainly free to do it. I'd be hesitant to start there. If I were you, I would start first with a more fine-grained lock implementation and then move to a lock-free implementation.
So the reason I started with a lock free is because if you go to a fine grained, you need to do all of the parallel stuff. But if you just go directly to a lock free one, then you can keep it on a single free list, and you just need to automatize the free and allocate operations. So it actually isn't that bad.
Yeah, I think maybe in if there's a single list in the case of the kalloc, that might be the case. I think the lock-free balloc is going to be a little bit more complicated.
Yeah, that I'm scared to do. But
okay, that's the right reaction to have. Anybody else?
I found it a bit hard to debug those problems because it's not immediately clear what is happening. So you have to go and sit with GDB and break, and yeah.
Yeah, I think one reason I'm always scared to get these lock labs as labs is they're harder to debug, and a bug may not show up on every run, and but hopefully it is very educational, because like learning programming locks inside of a kernel is a real thing, and but it is definitely a core challenge. One thing about maybe this is a note for the encouraging note. The next lab actually doesn't involve basically any concurrency, and should hopefully therefore be much more straightforward. Okay.
I guess how do you efficiently or effectively debug concurrent programs, like with all those multiple threads using GDB?
I use very basic stuff. I use print statements. But the main thing I rely on is I sort of try to write down or assertions for invariants that I think should be true at every point. And if the assertion goes off, then I know that there was something wrong in my thinking, or the assertion was wrong. And then I think for a while and try to decide what it is, and then go from there. In normal, for many other settings, there are race detectors that can help you, and again, basically flag code that looks like it might be having problems or is prone to race conditions. But that's a whole set of other tools that we're not using, and it's not that we could, but there's a little bit of a big step to actually get that all up and going and running. So that's the other mechanism that people use, race detectors, and basically flag any shared variable that is updated or read without actually holding a lock. No, that doesn't help you with deadlocks. Like for example, in this lab in the BCAS lock, you get deadlocks. Deadlocks tend to be easier to debug, correct? Because you can you get the panic, and then you can look at the GDB, the backtrace, and see actually what was involved in the deadlock. Does that make sense?
Thank you.
Okay. Another suggestion actually somebody posted on the feedback is, the classes, the attendance is getting a little bit lower than in the beginning of the semester, and I think we might be small enough or on the size that it may be perfectly fine to actually have cameras on. And so maybe I want to encourage you to, if you ask a question, to turn on your camera, and it will hopefully improve our experience as if it's in the classroom as opposed to in a virtual meeting. And you don't have to look at me. Okay. Okay, today's lecture. So today's lecture is going to be about crash safety in file systems. And this is not crash safety in its most general form. I'm really focusing on a particular problem, or a specific problem, namely that a crash or a power failure can lead the on-disk file system to be in an inconsistent state or an incorrect state. And what I mean with an incorrect state is, for example, a data block belongs to 2 files, or an inode is allocated to 2 different files. And so the scenario where this problem might sort of appear is, let's say, you're running make a pretty file system, interacts with the file system, reads and writes files, and somewhere, during, that thing, a power failure happens. Maybe your laptop ran out of battery, maybe the power just dropped, or to your house, and you reboot. The power comes back on at some point. You reboot the machine, or the machine comes back up, and then hopefully you get a prompt again. You run ls, and you hope basically that your file system is in a good state, in a state that actually can still use it. And so the particular failures or crashes that we're concerned about are basically power failures during file system operations, or the kernel panics, while running some file system operation. x86 has panics, most kernels have panics. Maybe there's some kernel bug that causes a panic, and then suddenly your system just fails. And what you'd like to be the case is that after reboot, you can actually do something, or you can still use the file system. And this might be something where you're thinking, well, how could that not be, right? Because the file system, is stored on a persistent storage medium, and so if the power fails, the medium should be good, and so when the machine comes back up, all the blocks that you've written should be there. And we'll see that the tricky case is that many file system operations have multi-step operations, and really what is important in those and if we crash just in the wrong place in these multi-step operations, the file system actually may end up being on disk inconsistent for that short period of time. And if the power failure just happened there, something bad could happen. And so that is sort of the problem that we're focusing on today. And so this is different from the problem that, for example, there's a power failure and your disk, caught fire, and so there's nothing there anymore. And so you need to, in that case, there's a completely different problem that has different solutions. For example, you have to go back to a backup of your file system, reinstall your file system, et cetera, et cetera. So that's the problem we're not worried about. We're really worried about the specific problem of failure happening right during a multi-step operation. Okay, and the solution for that specific problem that we're going to be exploring is something that is called logging. And this is a very popular solution. originally coming out of the database world, but a lot of file systems use logging these days. It's a very, one reason it's popular is because it's a very principled solution. And we're going to see the instantiation of logging in XV6. And of course, XV6 has a very simple implementation, like a bare minimal implementation of logging, just to sort of demonstrate the key ideas. And even that sort of very bare bone log implementation actually has some subtle issues that we're going to be talking about. And that's why it's worth studying it. One downside, as we'll see, of the XV6 solution is because of its simplicity, its performance is also not so great, even though logging systems in principle can get good performance. And so what we'll do next week is actually look how to implement a high performance logging system by studying the logging system that the Linux ext3 file system uses. But that's next week. Another maybe small point I want to make today is that this is our last XV6 lecture. And from now on, we're going to be switching to papers, because in some ways what we've done is we sort of covered the basic concepts, and we can start looking at more advanced operating system ideas by reading papers. Okay. Any questions so far? We're all good. Okay, so let me go back a little bit about like the scenario that we're really that we're focusing about in this lecture. So file systems or file system operations, like creating a file, writing a file, are multi-step disk operations. And we saw that last week or Monday. We talked about how create is implemented, like creating a file or writing to a file. And we often see that the sequence of events is of something of the sequence of steps are allocate an inode or mark the inode allocated on disk. Then write the directory block that contains that inode. And so those are the multi-steps that I'm talking about. And if we get a crash between two of these steps, that can that crash can leave may leave the file system invariance violated. And the invariants I'm talking about are invariants of the form, every block is either free or allocated to one file and not to two files. And we might want to make sure that this happens despite these failures right between these operations. And the risk is if those if these invariants are violated, that bad things can happen after reboot. You might crash again immediately because there's some data structure the file system is in now in a state that the file system actually can't really deal with. The on-disk data structures are in such a shape that the file system really can't process them anymore. Or you might, more likely, you not crash. No crash, but data may get lost, or you read or write incorrect data. And we'll see a couple of examples, to make that more clear. But so this is sort of the risk that we're worried about. I don't know if anybody actually ever in personal life or like in your daily life using computers actually has experienced this problem where basically you had a failure in the file system, or you had a power failure, your machine rebooted or your phone restarted, and basically it was unusable afterwards. And the one reason that might be unusable because is actually the file system just didn't recover correctly. Okay, so to make it more clear, let's look at an example in the context of XV, like to make this risk a little bit more concrete. Let's look at an example in the context of XV6 and to see what actually could go wrong. So remember from Monday that x86 file system, very simple file system. It has a simple disk layout. It's the super block. There's the super block. There's the log that we're going to be talking about a lot today that we didn't talk about on Monday. There are inodes, it's a set of blocks that actually contain each block may contain multiple inodes. There's the bitmap block, to record which blocks are free and which are not free. And then there are the data blocks that actually, contain the actual data of the file system. And if you remember from Monday's lecture, I reproduced the trace here. We looked at actually how a file is created. And, we see that the creation of a single file, hold on, let me a second. The creation of a single file consists of multiple operations. So, for example, like in this particular scenario that I have here on the slide, we see that an inode is allocated, and we know this because there's a block 33 is being written. Do we see that the inode is being initialized and then written again to block 33? Then we see that block 46 is written, and that reason it's written is presumably because the directory block that actually contains X and the inode number for X is written to the disk. Then the inode, root inode is updated to reflect that the directory has grown in size to contain this particular file X, and then the inode is updated. And so what we want to now understand is like what happens, like what could possibly go wrong, right? And so let's say we have a power failure like right here. So here is a power failure or a kernel crash. And so what happens after the power failure, correct? All the in-memory state is lost, right? Because that in-memory state, the data that's actually in RAM, like all the processes, all the file descriptors, all the in-memory caches are gone because memory is not persistent. And the only thing that we have left, right, is what actually is on the disk. So only the data structures and the bits and bytes that are actually sitting on the disk are survive the power failure because that actually medium is persistence or has durability. And so we want to know, like, we understand. So if we crash here and we have no additional mechanisms, or we have no logging, as that we're going to be talking about, but we have no additional mechanisms, how bad is it? What risk are we running here? Anybody? So basically, we've written block 33 to record that the inode has been allocated. Then we had a power failure, and then we come back up. Go ahead, Brendan.
Does that mean we lose the lose this block? It's like it seems like it's populated, but it's actually not.
Yeah, correct. I think we're losing we're not losing the whole block, but we lose the inode X, right? The inode X or the inode 4X that was allocated or that is marked as allocated is allocated on disk, but we have not put it in any. We've not succeeded, correct, in putting it in any directory. So basically, on the disk, there's an inode allocated, but it doesn't appear in any directory, so we can't even remove it, right? And so basically, what will this cause us to happen is we lose an inode. Does that make sense? So you might think, well, what I should do is like maybe I should reorder the writes, and in a way, that hopefully, this, we don't lose the inode. So, for example, another thing we could try doing is say, well, what we'll do is we'll write 46 first. And basically update the inode, update the directory, write the directory inode, write 32, and then we'll actually mark the inode as allocated on disk to mark it as indicated, to mark it as allocated. So we do the same set of operations in a slightly different order, in the hope that we avoid this losing of the inode problem. And would this work? Well, the thing that we should do, ask ourselves, like, let's think about this point in time. let's say a crash happens like right here, or power failure happens right at between updating the directory basically, but before we allocated the inode on disk. And now, we power fails, machine comes back up, and we look at the file system. What state will the file system be in?
It'll still think it's a free inode, and
Yeah, what would happen if, for example, we read, the file X in the directory, in the root directory, because it is in there now, correct, in this data block. We're going to be reading the inode that actually is not even allocated, correct? It's marked unallocated. And worse, what could happen is, correct, that inode might be allocated again, or it might actually really be allocated because it's marked as unallocated to actually, in fact, a different file, correct? And so now we have two files that might actually, the two files that actually share, even though they're completely different, they share the same inode. And so, for example, if one file would be owned by user 1 and one by user 2, then basically user 2 could read user 1's file data, right? So that's no good either, right? Does that make sense? So basically, switching the order, is not really going to solve our problem. You would just basically get a different problem than we had before. Okay, let's look at one more example. Here's the example of writing to the file X. So once we have the files allocated, let's say that all succeeded, and now we're executing the write system call. And the write system call also does multiple writes operations, as we saw on Monday. Example, it will allocate a block, in this case block 45. So it sets a bit in the free map. Okay, the block 45 is the bitmap block. So it allocates a block in the bitmap. It allocates a bit in the bitmap block to indicate that that block has now been allocated. That block turns out to be, I guess, 595. And then we write, the character H, to 595, and then the character I, and then we update the inode. And now we can ask ourselves the same question, like, what will happen if we crash? So, for example, let's say we crash like right here between, writing the bitmap block, but before we allocate, before we actually write the inode. So crash here. And so we reboot, we come back up, and the disk is in a particular state. And what is the risk?
We use a data block, but we lose it.
Yeah, we lose it again, correct? Because the block is allocated, but it doesn't show up in any file because it hasn't been written into any inode. So we lose a data block. So you might think, okay, well, maybe, just because we wrote them in the wrong order, what we should have done is, actually first write it in the inode. So first write 33 with the, with 595 as in the, either as in an indirect block or a direct block. And then, actually we will mark the inode, the block is allocated. So we'll write, 45. Right, so we change the order because we want to avoid these lost data block, and we change the order in this way. And now let's consider the case if there's a failure right here. What is the risk?
The size of the file is not compatible with actually how many data blocks are allocated.
That might be, although I think in the write of 33 actually updates both the size and the block number, correct?
Oh yeah.
So that might work out okay. If there were two separate writes, that would be a problem. But there's some bigger problem here.
It's that the file has things that it has the data block, but the data block is marked as unallocated, and other files can also use it.
Yeah, correct. Now, that's the real big problem here, is that the inode thinks the block 595 belongs to that file, but actually on disk, it's still marked as unallocated. And so when later another file is created, that block actually might be used for that other file. And so now certainly one file thinks it owns 595, but actually another file does. And in fact, both files will have 595 in their block numbers for their inode. And basically, if one user owns that file and the other user owns the other file, they can actually read and write each other's data, right? And it's clearly not what we want. The file system should guarantee that every block only belongs in one file and no other file, or is free. Okay? So this could lead to security problems, but basically block is shared among multiple files. And that's definitely wrong. Does that make sense in terms of the problems that can appear? And again, the real issue here is not so much the ordering of the writes, but the real underlying problem here is that we're just doing multiple writes, and they basically have to sort of show up on disk as an atomic operation. Okay, and so the solution that we're going to explore in this lecture is logging. And as I said before, this is a common solution used in file systems, and originating actually out of the database literature. And it actually has a couple of good properties. One, it's going to make basically system calls or file system calls atomic. With that, I mean, so if a create file, or you call create or you call write, basically all the effects of that system call just all appear all together, or none of them. And so that avoids this sort of problem of only some subset of the writes actually showing up on disk. The second good property it has, it allows for fast recovery. So after reboot, turns out we don't actually have to do a lot of work to repair the file system, actually a very minimal amount of work. And this is in contrast to some other solution that I'm not talking about, which is basically you go and inspect the file system, and maybe you read all the blocks of the file system, or read all the inode blocks, read all the bitmap blocks, and so check out whether the file system is still in the correct shape and maybe repair things. Logging has this nice property that actually the recovery is fast. And then finally, it is in principle, it can be actually very high performance, although the one we're going to be looking in the context of XV6 is not high performance. Right? So we're going to look at that next week. We'll see actually how to build a logging system that has atomic file system calls, fast recovery, and high performance. Today, we're going to be just focusing on the first two. Okay, the basic idea of logging is actually straightforward. And so basically what you do is you divide the disk in sort of two pieces. One is the log, one is the file system. And the file system might be much bigger than the log. And when you need to update the file system, so update, let's say, block 33 or update the bitmap block, we're actually not going to update the file system blocks. So we're not going to update the bitmap block directly. Instead, the only thing we're going to do on the right is, so here's our memory. We have a block in memory. This is, say, the bitmap block, like it's 45. And instead of writing it to 45, what we normally would have done, what we're going to do is actually we're going to write it into the log. So we're going to stick it here. And remember that actually should go to 45. We don't put it there. And we do that with all the other writes too. So for example, we'll put our inode block there. That was like maybe 33, I think, if I remember correctly. And we'll stick it in there. And we'll remember that it actually has to go to 33. So basically what we do, any write is first logged. And so we don't write directly to the home location of the block, but we just put it always in the log. Then at some point, when the file system operation is done, for example, it has these 4 or 5 writes that we saw in the previous slides are in the log, we commit the operation. And basically what it means is somewhere in the log, we just record a record, in a fixed location that basically says, okay, well, there are like 5 blocks in the log, and that is, the log set of logged writes. And then, when we have all the writes stably on disk, we're going to actually install them. So this is called the installation phase. And really what that means is we're going to move, these logs from the log to their home location. So we know this one has to go to 45, so we'll put it at 45. This one has to go to 33, we port it to 33, et cetera, et cetera. And once we're done, basically we can clean the log. And cleaning the log is basically rewriting, basically setting this 5 to 0. And that is the basic plan. And why is this plan good? Well, let's think about it. Let's say we crash before here. What would happen? So let me hold that question. Let me actually talk about one thing before asking that question. Let's say we crash. And so we reboot. And on the reboot, there's basically what the file system does. It looks at the commit record, sees what the value of the commit record is. If it is 0, do nothing in our simple scheme. And if it's like bigger than 0, we know that there are basically blocks in the log that need to be actually installed. And we apparently didn't finish the installation. We crashed, after the commit, but before cleaning the log. So basically we reinstall. And after we reinstall, we clean the log. Okay, and this scheme is good because it actually ensures that no matter where a crash happens, we either install all the blocks of the writes or we install none of them. But we're never in we'll never end up in a situation where we installed some of the writes, but not all of them. And just to see why this is true, let's consider a couple cases where the things could crash. So things could crash at between 1 and 2. What will happen? In what situation do we end up?
Situation in which on recovery we do nothing, and that's okay because nothing has been written to the file system yet.
Yeah, no, exactly. So this is the case where basically we just do nothing. As if the system call would basically never executed. Right? It's as if the failure happened slightly earlier, right before the file system call started. And so that's perfectly okay. That's acceptable. Okay, what happens if we crash? Okay, between after committing but before we installed?
Then you'll just redo all the installs, so you'll kind of restore the correct state for the
Yeah,
file.
so exactly. So at that point, correct, we know there all the blocks are in the log. They'll be all written because we committed. So it must be the case that the whole file system operation finished. And so we can basically put them in their location where they should be. And then we're all in good shape. And so in this case, all the file, in this case, what will end up is as if the file system call actually completed just before the crash. There's like no difference. Okay. So what happens if we crash during reinstall or like in install or during install before recleaning? So crash here. We did this case, we did this case, and now we'll do the third case. We'll install during installation or just before install, after installing, but before cleaning. What will happen then?
On
It's
the-
same.
Oh, sorry. On the next restart, nothing has really changed in terms of the recovery process.
Yep.
And so we're just going to redo the log.
Yeah, we're going to redo the log again, and we're going to copy basically the content again, to the locations, right? Maybe. In fact, we might do it multiple times. Is that okay?
Yes, because those are just writes, and they are to a specific location that we don't change. Like it's written in the log, so we know where we should write every time.
Yeah, basically every time we'll do the same write, correct? So let's say in block 45, there's the value 10, and we're just going to write 10, to location 45 every time. And that's exactly what it should be. And repeating that right multiple times doesn't really do any harm, right? Because we're writing the same value that actually should be there anyway. And so it's perfectly fine, for us to do reinstallation multiple times. Of course, we shouldn't serve any other file system calls at this particular point in time. We should do this before we restart the file system. But while, during reboot or during recovery, we can just do this, right? Another way of saying that is that installation is basically idempotent. You can just execute it many, many, many times, and it will have the same effect at the end.
Question about that?
Yeah.
Because the interface is just read and write, if we had an append, this would not be safe, right?
Yeah, well, you can make append safe too, more fancy logging schemes, but for this particular logging scheme, we don't have to worry about that. In fact, like in some sense, the append is a file system level operation, and at that level, we can make it atomic using the logging scheme that we have here.
I see. Thank you.
I also have a question.
Yep, go ahead.
What would happen if the file system crashed while you were committing? So you want to like execute multiple writes and then you only commit like half of them.
Yeah, okay, so can you speak up a little bit more because your volume is low.
Oh yes, sorry. So if you wanted to like commit multiple writes at once, like in an atomic way, but your system crashes in the middle of committing, so you are only able to commit like half of the writes, what would happen in that instance?
Okay, so there's a very important point. I'm glad you asked the question. So first of all, you commit, writing this commit operation here, correct? This, step 2, you only execute that commit operation after you already logged all the writes that you were planning to execute, right? So at the point that you do the commit, all the writes are in the log. And so the commit operation itself, is an interesting question, like what happens there? So the way I sort of indicated this on this slide, the commit operation writes a single block, like a single sector on the disk. And the standard assumption that file systems make is that a single block write or single sector write is an atomic operation, meaning that if you write it, the whole sector will be written or none of the sector will be written. So the sector will never be written partially. And so there's always, clearly, valid data in that particular sector. And so basically this operation, that commit operation, writing the log header or writing the commit record is the real commit operation. Like if that succeeds and there's basically, say a 5 in the commit header, we know that there are 5 blocks in the log and we have to reinstall those 5 blocks. If the commit header didn't make it to disk, then the value will still be 0. And we'll just treat it as if the transaction never happened.
Thank you.
And the key rule that you're sort of hinting at that actually has to be true is something that's called the write-ahead rule, which means that a logging system cannot install writes until all the writes are in the log. Any more questions about this sort of basic plan? Okay. Good. Let's see. So what I'm gonna, there's many different versions of logging schemes, and I sketched out here a very simple one. It's perfectly fine. There are schemes where basically the cleaning of the log is postponed, installation is postponed until later. But I'm just going to run sort of with this very simple scheme, and then on next week we'll see more sophisticated logging protocols. But all those logging protocols follow this write-ahead rule that before you write the commit record, you have to make sure that all the writes are in the log. But then there's a lot of within that still there's a ton of flexibility in designing a particular logging protocol, as they're typically called. Okay. I'm going to look a little bit how this then is manifests itself in XV6, as a sort of a case study and to make things really concrete. Okay, so in XV6, there's sort of, we're going to look at 2 sort of pieces of state, if you will. The stuff that is actually on disk and that is things that are in memory. And the in-memory contents will disappear on, or the way we should think about it is that the in-memory contents will disappear on a crash or a power failure. And the structure of the xv-sig log, as always, is extremely simple. We have one block at the beginning, that's the header block, and that is basically our commit record. It contains the number n, which is like the number of blocks in the log, and then for each block, the block number, the home location of that block, blah, 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 blah. So there's going to be n of those. And so then in the log itself, R basically is the data for that, belongs to that. So here's the data of bn0, here's the data of bn1, etc. to bn-1. So that's what's in the log. And that's the only thing that's sort of in the log. There's nothing more to it. Then in memory, while the file system is running, there's an in-copy version, or an in-memory version of the header. And it basically has the n, and it has an array of block numbers, etc. And then, these block numbers refer to blocks that are sitting in the data that actually corresponds to the block numbers that are sort of sitting in this in-memory data structure. They live in the block cache, which by now you're well familiar with. And so maybe this is like block 10 is the first block in the log, or let me take a more concrete example from that lines up with our previous thing. So maybe this is like 45. And basically, somewhere in the in cache, in the block cache, there's of course, whatever block for 45. And here's its data. Okay. And that's sort of the structures that the on-disk, the in-memory file system has, and the on-disk file system has. So the on-disk file system just has the log. The in-memory has these data structures to orchestrate these multi-write operations that we're going to be doing. Okay. So to make this a little bit more concrete, let's look at some code, and that will help us understand how everything works. So let me pull up some code, and let me put this next to it. Let me keep that picture so that we can look at it if we want to, or I can point to it. Can everybody see my code?
Yeah.
Somebody have to confirm that they're seeing the Emacs window.
Yeah, we can see it.
Good, good, good. Is it big enough?
I think it's good.
Yeah.
Okay.
Yeah, looks good.
Okay, thank you. Okay, so let's start with the, I talked about transactions, right? The fact that, we should not commit until, we should not write a commit rather until all the writes have done. And so that means that your sort of file system operations must indicate sort of what the beginning of the transaction is, and particularly what the end of a transaction is. And the way that happens in xv6 is that every file system call, here's open, that corresponds to create, basically starts with begin up. And begin up basically indicates like, okay, I want to start a transaction, and I want all the block writes that I've been doing between begin up and end up, which is basically at the end of the transaction, to be atomic. Meaning, they should be all applied, or none of them should be applied. Okay. And so every file system call in xv6 has that structure. That basically has begin up, then the code that implements the file system call, and then end up. And that end up is basically where the commit operation happens. So basically between begin and end up, the on disk or the in-memory data structure should be updated. Whatever the in-memory log may be updated, the block cache might be updated. But nothing really happens until end up, and at end up time, we're basically going to put things into the log, and then if we done with putting everything in the log, we'll actually write the commit record or the log header. Okay, so let's. So what is interesting, of course, then what happens is every write, correct? Like whenever one of these file system calls does a disk write, something must happen. So if we go back, for example, to fs.c, look at ialloc. Ialloc, basically what it calls, it doesn't call bwrite directly, but it actually calls logwrite. And so we're going to see what logwrite does. So, and the logwrite is basically a function implemented by the logging system. And every write that basically a file system call does between begin up and end up always goes to logwrite. And so here's logwrite, and logwrite actually is reasonable, straightforward. We've written the block in the block cache. So somewhere basically you have 45, maybe this is like the write to 45. We've updated 45 in the block cache. And now we're basically going to record in the in-memory data structures that to some point later at commit point, we need to write this block into the log. And so, basically, the code is, the code is reasonably straightforward. It acquires a lock on the header and basically updates the header. And in particular, what it does, it goes through, it updates n, where actually the first thing it does, it actually sees if there's already a copy of 45 in the, if 45 is already recorded as being having to written to. And if that's the case, nothing has to be done because 45 will be written to. And so we're done. And this sometimes is called log absorption. If, block 45 is not in the array yet, or not in the list of blocks or the array of blocks that needs to be written to disk, then basically, the only thing this particular piece of code does is basically bump up n and stick, that block number that needs to be written into the next entry or into that entry. Then the only other thing it does, and I'll talk about this later, it will pin the block in the buffer cache. And let me postpone why for a little while, but I will come back to that later. And that's actually all what logwrite is doing. So every file system call that needs to update a block, updates the block in the block cache, and then basically appends it to this in-memory data structure, unless it's already there, in which case it just absorbs it. Does that make sense?
So
Okay.
does that mean that bwrite shouldn't be used by itself at all?
Sorry, say again.
Bwrite shouldn't be used by itself, only as
Yes, that's correct. Yeah, basically one way to think about it is that every bwrite in the file system is replaced by logwrite. Okay, so now let's see what actually happens at end op, correct? Because that's where the exciting part happens. And there's a couple of cases that I just want to avoid talking about until a little bit later, because they, even this simple logging system actually has some subtle complexities, and most of the beginning of this code deals with these subtle complexities. But I just want to really get the normal case, there's the simple case where no other file system operations are in progress. We execute, create file, and basically we're getting to the point where we want to commit it. And so the code is pretty straightforward. It calls commit. And so let's look at commit. So here's commit. And basically commit does two steps. And basically it writes the log. And that's basically writing all these block numbers that are sitting, in the in-memory header, and writes them basically all to the header on disk, including, this number n. Correct. And so let's see. That's what write head does. Sorry. Write log basically writes, the blocks from the buffer cache into their respective, or into the log itself. So let's see what write log is right above here. And you can see what it does. It goes through, this array, one at a time, and basically writes that to the log position in the log. Okay, so it reads, the log block, then sticks it in there by copying it and then writing it actually out to the disk. So this basically ensures like block 45 will end up here. You know, so let's say this is 32, that will end up there, et cetera, et cetera. Then in the end, so at this point, we have not committed yet, correct? The only thing we've done is basically putting blocks into the log. And if we were crash at this particular point in time, you know, before, you know, calling write head, before write hex succeeded, then basically as if the transaction didn't execute at all. So let's look at write head. So that write head is, you know, what I called earlier, basically the commit point. And the commit point basically, you know, it's basically straightforward. It reads the header block from disk, which is probably sitting in the buffer cache. It, you know, copies the n, you know, this n into that block, puts all the block numbers into that array, into that block, and then basically writes that particular block. So this is this B write. What is that? Is that the commit point? If a crash happens before this B write, what happens then? Anybody?
If the crash happens before B write, isn't the only modification that we've made to the in-memory HB data structure? So it's going to be fine?
Yeah, it's going to be fine, right? Because basically we may have written DB10, DBN, or whatever to the log, but we have not succeeded in writing the log header. And so we'll do not, on recovery, nothing will happen. And what happens if there's a crash right after the B write? So like a crash here.
And it's no longer 0, so the log header is correctly read and it's recovered.
Yeah, it will be recovered, correct? Well, at some point, hopefully during recovery, as we inspect that, you know, we expect that recovery will actually read the log header, see that there is a 5 in there, for example, and then copy the first 5 blocks to their home location. So this is really, this one line, this one disk write, this one sector write is really the commit point, correct? Before the commitment point, the transaction is as it is. The transaction didn't happen, and after the commit point, the transaction will definitely be finished, assuming recovery is correct. Okay, so let's go back to commit. So commit, after it's committed, it actually installs the transactions, and that's pretty straightforward. Basically, it takes the blocks, looks at the header where that block belongs, and then basically writes it to that particular location. And so we can actually look at the install trends and see that actually that's what it does. It has a copy of the log header, and it reads the log header. It reads the destination block, the home location, copies the data from the log block into the destination, and then writes the buffer to the destination. Okay, so basically, effectively, what this does is basically, if you go back to this previous slide here, it copies, it just does these copies from the log into the home location, or actually in the file system. And of course, we might get a failure somewhere in, this code or while we're doing this, but that should be okay, because hopefully on recovery, we'll just start over from the beginning. So let's look at, so that was install. So once install is done, then basically it sets the in-memory header n back to 0, and then writes that log header. And effectively that causes to cleans the log, because basically there's now 0 in it. Question? Parker.
So you, the function you're in just before, like whereas does the from to or to from getting, so that puts the block that you're going to like update, the log block that you're going to update into the buffer cache. Could you make it faster by not putting it into the buffer cache and just directly writing it to the device instead?
Let me, so which function we're talking about?
I forget its name. It's the one where you copy everything into the log.
Okay, install all. install trans.
I think so.
That
Yeah.
this one?
No. Maybe it was this one.
So this
I was
basically-
thinking probably of right head, but it's the same thing.
Okay, the only reason, the only reason to this, basically our interface is not particularly good. You could just write straight, you're wondering why you are doing the read. There's no reason to do the read because we're going to write anyway. Is that the question?
Yeah, that, and you're also doing the mem move, right?
And you didn't move, yeah. So this actually, a sequence of code can definitely be optimized. You can save, 1 or 2 disk writes. Just for simplicity, we don't do any of that.
Okay, thank you.
Okay, so I think we're in over commit. Just go back and double check. So we did the right log, we did the right head, and basically this is the cleaning operation. We erased the transaction by sending it to 0. Okay. So then the only thing to sort of further inspect is like how does recovery work? And so recovery happens when when XV6 starts. So now we had a crash, correct? So the system failed. We rebooted, and one of the first things one of the things that XV6 does during initialization, it actually calls init log. And init log basically calls this function recover from log. And so let's see what that does. And basically recover from log, calls read head to basically extract or read the. Let me see if I can scroll down here a little bit. Yeah, basically reads the header from disk and sees if n, well, it doesn't really see if n is 0 or not, but it just calls install trans. And this is exactly the same install trans that we just looked looked at a little while ago. And basically, it looks at this n and installs all the blocks from 0 to n out of the log into their home location. And if it's done, once it succeeds, then actually it calls clear log as before. And so that's actually all what recovery does. Recovery just basically always does the installation. And if we crash during installation here, no particular problem again, correct? Because we'll crash, we'll boot. XV6 during booting will call log init, which will call recover from log, and it will basically reinstall or replay the log, as sometimes called, again. And this might end if we crash every time, or many times. It will reinstall or replay the log many times until hopefully at some point it succeeds and actually gets the whole log written or gets the whole log installed to the home locations. Does that make sense?
Oh, I had a question about, so if a process just runs normally, it writes some data to disk, and then at some point after that, before it commits and installs the changes, there's a failure.
Mm-hmm.
The process, from the process point of view, nothing happened, but something like, I guess the failure happened after the process ended, what it was doing. So is there anything bad about that?
I'm not 100% sure where you're getting at, but the short answer is there's nothing bad, right? Because the disk won't be updated at all. So it's just as if that file system operation didn't happen.
Right.
The process,
Or I guess I'm saying
the process
if there-
disappears too, but we don't expect the process to survive failures anyway.
right. Or I guess, okay, I think that answered my question. Thank you.
Yeah, it's important to remember that basically the only thing that really survives failures or that's persistent across failures is the disk or the state on the disk, nothing else, right? Okay, so just to make this all concrete, one little bit more too. Let's. I put a statement in bwrite, so actually the thing that actually does write to disk, like in the block cache, and we're just going to see what the trace of actual disk writes are. because basically on Monday, I sort of, I didn't tell the full truth because basically I put the print statement in log write and not in B write. And so now I put it in the B write, and so we can actually see all the blocks that are being written. So we'll do the same thing as before, echo high X, and just look at actually the actual disk writes and see if they make sense. So the first thing to note, correct, is that this trace is way longer than the trace that we looked at last time. In fact, that we looked at slides a couple slides ago, right? Because if you look, in fact, just to demonstrate this, here was that same echo high, correct? And what we see there is like only, it's 5 log write operations, but it turns into many disk operations, correct? So let's look at it. So what we think B write 3, 4, and 5 are, and what is B write 2? Anybody?
Is that writing to the log and then the super block?
Not the super block, but
Right.
you're right.
No, that's sorry, the log head.
Yeah, so
Yeah.
just to look at, you got it right. Just looking at this picture again, correct? The log starts at 2, so that's probably the header block, correct? The commit record, if you will. And then 3 is the first data block, 4 is the second data block, 5 is the third data block, right? So going back, this is the first write, the second write, the third write. They're all going into the log, and they're written to disk in the log part of the disk. And then this is the commit record, the header. And then presumably, what is this phase? What is this part?
Is that the bitmap setting?
No. So what do we think actually is stored in this B write 3?
Here, aren't you creating the file, the inode for X, updating the
Yeah.
directory, and then also actually making the file itself?
Yeah, and so and we didn't do it here, correct? Because in these B writes, that didn't happen. But now we're doing it. So what phase is this of the transaction?
Installing the changes?
Yeah, it's installing the changes, correct? What we did here is we logged the writes, then we committed the file system operation, the create operation, and now we're installing it. So now we're putting the blocks in their home location. And now, and what is this B write 2 then?
It's clearing the log.
Yeah, it's clearing the log, exactly. So basically the system call was writing 33, 46, and 32. And to actually do that using the logging system, that basically turns into this set of disk writes. Right, where the first part is the installing the log, if the first part is actually logging the writes, and the second part is installing the log. And these are the 2 writes to the commit records. Does that make sense?
Is it possible to infer where begin op and end op would run from this trace?
Well, so we sort of know, correct? So where did, we don't really know where begin op start, but it is at the beginning, any file system call starts with a begin op. And it must be the case that the commit record, correct, is written in end op. So we know that this is the end op of some file system operation. Does that all make sense? Okay, so that was basically x86 logging and logging in action. And I want to talk about a couple complications. And even this dirt simple, naive logging scheme actually has complications. One thing to immediately note, of course, is, is this a very performant implementation? Just by looking at this trace.
No.
Yeah, why not? I know this is basically a too simple question, but it's important to ask.
Like, you're writing the stuff twice, right?
Yeah, you're writing your stuff twice. So if I ever write a file F or a big file F, I'm going to write that big file F twice. And so certainly not particularly high performance, right? I mean, basically we're cutting the performance immediately by a factor of 2 just to get crash safety. And so we'll see on when you're reading the ext3 paper for Monday, one thing you should keep in your head is while reading is how do I get around sort of this factor of 2? Okay.
Sorry, is it the case that you write the H and the I separately?
Yeah, I think so.
Okay.
I'll show you in a second why, what is happening there. Or maybe, well, let me not commit too much to that answer, but I'll come back to it.
Oh, sorry, am I having the empty line, not the H and the I, but yeah.
The new line is a separate write. The H and I
Yeah.
is just one write, and the new line is a separate write.
Okay, thank you.
You're welcome. Okay, there's complications, and I want to talk a little bit about these complications. So okay, here's our basic scheme and basic data structures, and there are 3 complications that I want to talk about. Or maybe I will call them challenges, whatever you want to call them. The first is eviction. And the issue is as follows. Let's say we go back to this picture here, and the whole B cache is full. And so the transaction is in progress. Let's say we just updated 45. It's now done with block 45, so it's going to write the next block, and the cache is full. And let's say we don't have a solution for this yet, but the cache decides it wants to evict 45. Correct? And if it wants to evict 45, that will mean we have to write it to its home location, right? How bad would it be to write the block, evict 45 and write 45 to home location? Is that good or bad? Would any rule be broken if we did that?
I guess
Oh, sorry,
that
go ahead.
is if a crash happens before the other writes in the same transaction occurs, then basically atomicity is broken.
Yeah, so this is bad, correct? Bad, this basically violates this write ahead rule that I talked about. You have to write all the blocks to the log before you write any block to its home location. So it has to be the case, correct, that the cache does not evict any block that sits in the log. Does that make sense? So the solution is don't evict blocks that are in the log. And this is exactly what you were showing a little bit earlier and said I didn't want to talk about. So if you go to log write, again, just to see for a second there, log write, here's log write again. And here we see this call to bpin. And what do you think bpin does? The name sort of indicates it.
It pins the block in the cache.
Yeah,
So
and how does it do it? Since you've been looking at this for your current lab extensively, what do you think it does? So we can look up the implementation with bpin, but we can also guess what it does.
Doesn't it essentially just make it so that it doesn't get evicted by increasing the ref count?
Yeah, exactly. This is the only thing it does. Bpinch just increases the ref count, and we know from the Bcache code, correct, that evict won't evict any blocks we have a ref count higher than 0. And so presumably somewhere later in logging code, when once actually everything is logged, we can actually unpin the block, correct? Okay, so that's one complication. So we have this pinning and unpinning going on. Let's look at another complication. The file system operations must fit in log. If you see, if we go back to our picture here, or actually maybe this is the better picture. How big is the log in x86?
blocks.
Yeah, 30 blocks, 32 minus 2. So, the max log size is 30. Of course, we could bump it up, and, real file system runs with a much bigger log, but it doesn't really matter. No matter what, it has to be the case, correct, that the file system operation must fit in 30 blocks. Because if a file system operation would try to write more than 30 blocks, that means we would have to spill something to the on disk location, and we're not allowed to do that, correct? Because that would violate the write ahead rule again. So it has to be the case that every file system operation fits into the log. Does that make sense? And in fact, how do you think we got to 32 or 30?
Does it have to do anything with how many blocks actually fit?
Yeah, or another way to find, because basically, how many blocks what is the maximum number of blocks, correct, that a file system operation could write? And that is really what this number 30 has to be definitely bigger than any, the max number of blocks the file system operation writes. And so, in fact, what Robert and I did is we went through all the file system operations, looked at them, and decided whether what sort of the maximum number is. And it turns out the maximum number is much lower than the 30. But we'll see in a second. There's a couple interesting complications. Like for example, the operation that we've looked so far, like creating a file, correct, is only a handful of blocks. The file system operation is like 5 blocks. And in fact, most operations are a handful of blocks, not that many. Can you think of any operations that might write many, many, many blocks?
You mean write on a huge file?
Yeah, write a huge file, right? So what if we, call the write system call and we pass it a buffer with like a megabyte of data, right? Like 1,000 blocks. It seems like we're being serious trouble, right? It would violate, this maximum rule. And so let's look at write. Write. This write calls file write. So let's see if it's file write. So here's file write. Okay, so here's this is an inode, a file descriptor inode. Everybody can see my code, or the code that I have on the display. And notice that what does this code do? You can read the comment right on top, here, and then it basically explains it. But basically, what happens, correct? The write is split in many number of smaller writes. So what really is going on here, correct, is we're ensuring that the whole write as a whole is not atomic, but that's okay. The right Unix system call semantics don't require that actually all the 1,000 blocks, of our megabyte are actually written atomically. It just requires that we don't corrupt the file system, don't corrupt the file system while doing it. And so basically we, x86 splits a big write in a number of smaller writes and writes them as individual transactions. And this one basically ensures that, for example, if a transaction allocates a block number because we need a new block as an intermediate block, or because we need a new block because we're going to write to it, then at least that part is completely atomic, and the file system will be never left in an incorrect state, violating any of the file system invariants. And so the write is just split in many smaller writes or many transactions. Okay. In fact, that's the main one that actually is write fs split in many transactions. Any questions about this? And note, because things are pinned correct in the cache, that means also that the block cache must be bigger either to the log size. Okay, so now the final challenge that I want to talk about is concurrent file system calls. And the issue is as follows. Just let me first try to explain what the problem is, and then we'll see what the solution is. So let's say we have our log, and we're writing, and maybe there are two transactions executing concurrently. And just imagine for a second that they write a lot of blocks. So basically T0 is executing, T0 is executing, they're all full. So here's the beginning of the log, here's the end of the log. And T1 executes some blocks, and et cetera, et cetera. And by the time we run to the end of the log, neither one is complete yet. So they both have still more writes to do. And at this point, can we commit any of the two transactions? No, we can't, correct? Because if we would commit a transaction that is partially done, then we violate the write ahead rule again, and the whole purpose of actually login doesn't work out. So it has to be the case that basically a number of concurrent transactions must fit in the log. In fact, all concurrent operations must fit. And so in the way, so this is sort of a challenge, correct? We have a file system call starting, and we got to sort of arrange that basically that we basically do sort of an entrance check. Before we actually let the file system operation go, we must check whether there actually is enough blocks still. If we have like n file system operations already in progress, we have to make sure that if we allow one more guy to start, that actually the total number of blocks they could write together actually fits in the log. And the way basically x86 sort of gets around this is it basically limits the number of concurrent file system calls. And the way it basically works is that in begin op, we just see how many outstanding concurrent file system operations are in progress. If there are too many in progress, we just stop the current file system operation. It just goes to sleep, and it will wait until all the other guys are done and have committed. Right? And all the other guys will commit together. In fact, at some point, T1, T2, they're basically done. Maybe T3 is in a 2, they finish, and then basically all these transactions in a single time, or basically are committed together. This is sometimes called group commit, because you're committing multiple system calls. All the ones that were concurrent in action you committed this together as a sort of a single big transaction, so that all their updates are visible, so that all their updates so that all their updates take place, or none of them take place. Okay. And we can see that, if we go to
A quick question.
Yeah.
Is the group commit, is grouping the commits necessary? Like, could you, say if one system calls finish first, just commit its transaction and then commit the other ones later, or is it like a necessary property?
You got to be very, very careful, because you remember one thing I didn't really state this explicitly as a goal early on, is that we basically execute the system call still in the right order, right? If a write, or if a read observes a write and then does a write, then it has to be the case that that second write happens later than the first write. And the reason this is a log, correct, is because that basically reflects the order in which the writes have happened. And so you can't really willy-nilly change the order of the writes in the log, because that may actually result into bizarre behavior observable by user programs. And so it has to be the case that basically you commit, the operations and transactions in the order they happened, and also perform the writes in the order they happened. And so in general, it's safe, it's safe to basically commit them all together. You're always in a good shape. Okay, good question, Joe. Okay, I just want to go back to one more thing and look at the begin op that I talked a little bit about. Said like, oh, nothing, I don't really want to talk about it right now. But there we can see, so here's the game op. First of all, if we're already in committing the log, we're just going to wait until the log has committed, because we can't write to the log while the log actually being installed. If we're the nth concurrent operation that basically makes us go across that log size, we could just go to sleep and wait until basically all the preceding concurrent transactions are done. And if we're allowed to proceed, basically our entrance is allowed, we increase log outstanding by 1, because that reflects our thing, and then we basically proceed and start doing file system operations. And if you now look at end op again, just to see, you see that end op basically decreases log outstanding by 1, because one transaction has finished. It certainly would be an error if we were in committing state, so we panic in that case. If we actually are the last one from that set of concurrent transactions, then actually, and log outstanding goes to 0, we immediately start committing. And then when we're done, or when actually, if we're not the last, we commit. And if there's space, left, we wake up a guy so that they can actually start running. Okay. So even this dirt simple file system that, or this dirt simple logging system that XV6 actually has a bunch of complications. So I'm starting to run out of time, so let me wrap up here. So in summary, what we talked about is basically logging as a solution for crash safety, or really for multi-step file system operations. And what we've seen so far, it works great for crash safety, but performance. And that's going to be the topic for Monday. And as you read that ext3 file system paper for Monday, that's the thing you should be thinking about. Okay, any more final questions? And in fact, anybody who has to leave, please, feel free to leave. But if you want to hang around and ask more questions, please do so.
Oh, I have a question regarding cache size and the log size.
Yeah.
So you said that the cache size has to be at least as big as the log size, but they seem to be the same size for this case. So would that mean that if the log pins 30, buffers,
Mhm.
and then some other operation tries to do something, it just fails because it runs out of free spots in the buffer.
No, maybe let's look at the. Okay, so let me first actually check one thing. Okay, let's go to bio. Okay. Let's actually first check if nbuff is bigger than. Okay, it sets the max block size of the block cache. Okay, so it's set up to something big. So what happens actually if we can't find bcat can't find a buffer? It actually just panics. And so if there's no free slot in the buffer cache, x86 panics. So that's not particularly ideal. In fact, it's terrible. And so you hope never to be in this situation, and hopefully we picked our numbers correctly that basically this is unlikely to happen. But why can't we return an error? Because that seems like the obvious thing to do. Like, you just return an error to the caller, and then the caller maybe returns back up to the file system interface, and just returns -1, saying like, oh, this operation failed. Why is that a problem? So the way to think about this is that many file system operations are multi-step operations, correct? As we have seen now in this lecture and in the previous lecture. And let's say we did 2 writes, and then the third write we run into this case where we can't actually do the write because there's no place in the block cache. But we have done 2 writes, correct? Can we just bail out of the file system call?
Okay, I see. Right.
We cannot, correct? Because we might have updated in the directory, a directory block of some file. We might have updated directory block of some directory. And if we wanted to make this work, what we would have to do is basically undo those changes, correct? Like any writes that we did before as part of that system call, we have to undo.
Right. Okay.
And
right.
that is painful.
Right.
And so we don't do it. Does that make sense?
Okay, so it's not a problem if the log pins everything and there's no more space for cache, but it will just panic. Okay.
Yep. Yeah, of course, this panic should never really happen, right? Like there's only odd corner cases where that hopefully happens.
Right. I guess if you just, okay, yeah, that makes sense. Okay. Thank you.
You're welcome. Any more questions?
I had a question about, I guess following up on my earlier one about the group commits.
Yeah.
I was trying to think of, like, I think I kind of understand it at a high level, but I was trying to make sure like I understand like a concrete example of why group commits is important. And is this an example that kind of demonstrates it? It's like, I guess I was thinking of like a situation where you have, say like, this might be convoluted, like one process generating a stream of like numbers like 1 through n, and then 2 processes consuming that. Maybe they're listening on the same pipe, and say like n like stops on an even number. One process is consuming and printing out the odd numbers. One process is consuming and printing out the even numbers. And if you didn't have group commits, so like the correct behavior is, and say they're printing it, or like they're writing these to the same file. And so the correct behavior would be at the end of all this, you would expect the file to have like an even number, like the last number. But if you didn't have group commits, it's possible that the second to last process actually gets committed after the last one, and so you actually see 9. Is this like a correct example of why this is important?
I think I have to think a little bit more carefully about it, but that is definitely the flavor of the problem that you might run into if you reorder system calls.
Okay.
Uh,
think I have a concrete example in the lecture notes. If you
Okay.
look in the lecture notes, of a shell command that really, behaves weirdly if you didn't commit the. This is not really an issue in some sense from group commit. It is really an issue that like the transactions need to be committed in order.
I see. And if you didn't have group commit, then
Yeah, and just like
transactions might not be.
some people might think like, well, what I should if you didn't have group commit, then there's a temptation to basically commit some later transaction because it's already finished, but the first one isn't finished yet, and to create space. But that's not a solution.
Okay, that makes sense. Where in the lecture notes was this example?
I think
you
there's a
mentioned?
shell command where it sort of illustrates that like ordering is important.
Okay.
It
And is that in
doesn't tie it directly to group commit, but it just basically makes the point that ordering of system calls is important.
I see. Is this in the text
Yeah,
lecture
the
notes on
text
the
files,
website?
yeah.